limits. Now let me try how we're going to find the instantaneous rate of a function at a point without having to draw the tangent line like we had to do last lesson, right? Because that's going to get cumbersome if we have very big graphs. So we're going to use limits. First, let's go over what the idea of a limit is. Now, the informal definition of it is kind of seen right here. If f is as close to as we'd like to some real number a for all x sufficiently close to but not equal to a, then we say f of x is the limit of a as x approaches a, and we write the limit as x approaches a. That's how you say this. This is actually the important part. The limit as x approaches a of f of x equals a. In that case, we say f of x converges to a as x approaches a. That's a bunch of math gobbledygook, right? All it's saying is this. If you have a function, and let's say there's some graph that looks like, I'll do some purple, that looks like this, but let's say the number 2 has an open circle and it keeps on going, and maybe it has a value at 2. At 2 it's like here. So that's the degree. So that's some set effect, right? What a limit is saying, hey, the limit of this function f of x as x approaches 2 is what? And what the limit's saying is, limit does not care what happens at 2. Right here it's blank. It's actually the value 3, right? Put a close circle in the wrong spot. Looks like it's over to the left. Over to the right, I should say. I know my left and right. I know the difference between left and right. There we go. Right, so the value, if I just said, hey, what's f of 2? You should say f of 2 is a closed circle is 3. But the limit does not care about that. The limit doesn't care what happens at 2. It just wants to care what happens as you're getting close to 2. What does it look like is happening? What's everything telling you is happening? If you're looking from the left, like you didn't look right here at the actual value. Just look from the left, you're like, hey, this looks like it's going to 2 on the y, right? Like that's where it looks like it's going toward, 2 on the y. If you look at it from the right, if you follow the graph on the right-hand side, it looks like it's going toward 2 on the right. That's what a limit is telling you. If you just look at what the graph is telling you, like what the values are saying around the number you want, that's the limit. What does it look like is happening at that value? And why is this important to what we're doing? Because remember, the whole idea is that we want to find the instantaneous rate of change of a graph that curves. Let's say we're trying to find it at this point here. Right there. Let's just call that point, just for sake of argument, like 6, 4 or something. Right? And before limits, all we could do is try to pick 2 points. So we'll use that point and like this point here. We'll go like, hey, we can find the average rate of change. That's 2 points. We can find the average rate of change. But we want to find the slope at just that 1 point. And you can't just do the slope formula. You can't just go y2 minus y1, x2 minus x1, and use the same point twice. We can't go 6, 6, 4, 4. It doesn't work that way. What we could do is to get draw more lines that are closer and closer. So we use these 2 points, and then these 2 points, and then these 2 points, and then these 2 points, and get the slope of the tangent line that's really close to 6, and then use the limit to look at it. And that's kind of the idea of using the limit. We're going to use the limit as we get closer and closer and closer to 6, and see what that limit tells us. What's happening as we get super close to 6, but we can't be 6, right? Like if we're doing the slope of, let's say this is x1, y1. If I did 6.2 minus 6, and f of 6.2 minus f of 6. And then we went closer and we're like, we're going to do 6.1 and 6. Right, and we're going to go closer and go like 6.01 and 6. Remember, f is just the y value. Actually, in this case, f of 6 would be 4 in my values here. Right? As you get closer and closer and closer, we can't do 6 and 6. That's 0 over 0, and you can't do it. You can't do slope of one number. But we could look at the limit as you get closer. What's everything telling us it looks like as you get close to this? Right? Because we can't do this. But the limit doesn't care. So we're going to do all these instead. Well, that's the idea of a limit. So that's why we need a limit. So the limit doesn't care what happens at the actual value. It just cares what happens to get close to the actual value. And then what this lesson's about is how you evaluate a limit. And I'll explain what this picture is for a second. But first, let's talk about the general steps, how to evaluate a limit just algebraically. So that's what we're going to do here. So let's talk about the steps. 1, substitute the limit value into f of x. That's step 1. Just substitute it in. Plug it in. Plug it in. here's what happened. If you get a number, done. So you get a number, you get 4, you get 5, you get 6, you get 0, you're done. That's the answer, that's your limit. Now keep in mind, 0 over any number, we'll put k instead of a pound sign, is 0. A number over 0 is undefined, which means the limit does not exist, which everybody goes crazy about because of Mean Girls. But if you get 0 over 0, then you have more work to do. So you're not done. Oops, that always happens. So, and I'll talk about the more work to do in a second, but that's the general rule. Is that if you're evaluating a limit with a number, so steps limit at a constant, all we're going to do is plug that constant in, plug your value in. If you get a number, you're done. So you get 30, 14, 1/2, doesn't matter. You get 0, you get something over 0, undefined, you're done. If you happen to get 0 over 0, that's a special quality. It's called an indeterminate form. Then you have more work to do. Now in IBSL, that more work to do. 99% of the time is just factor. Factor and reduce. And then substitute a number in again. So that's the process. Sublimit value into your k. So here I'm going to plug in 2, I'll sub in 0, I'll sub in 3. If I get a number, I'm done. If I get 0 over 0, which is a special indeterminate form, you have more work to do, which in IBSL is only going to be factoring. So you factor it, cancel stuff out, and then you substitute your number back in, and then you're done. This portion right here is where you go in way more detail if we're taking HL or if we're taking AP Calculus. There's a lot more different ways to fix the work you have to do. The more work you have to do gives it more detail. And HL and AP Calculus. But in SL, you just factor it. That's what's going to happen. What does factoring do? So that's what this picture is about. So if we're going to substitute in 0 for this case, actually we'll get to this in a bit. Let's do a few examples first. So let me hear. Right, the limit as x equals 2 of x squared. So all we're going to do is substitute 2 in. I get 2 squared, which is 4, and there you go. That's my limit. My limit as x approaches 2 of x squared is 4. If you're wondering what does that mean? Look at the graph of x squared. Looks like this. And as you get close to 2, your graph's going to go to 4. Now, there's no issue with this picture. This picture, like literally the graph of 2 is 4. Everything's telling you it's going to 4. The actual value is 4. Plug it in, you got 4. That's the limit. No problem. When you plug it in, it doesn't work. When you substitute it in, it doesn't work like the next one. I get 0 squared plus 3 times 0 over 0. I get 0 over 0 in this case. Right? In that case, that's the special case where you have more work to do. So what is that more work? That's what I'm going up to here for. This was the exact same issue. If you substitute in 0 to this, you get 0 plus 0 over 0, you get 0 over 0. You have more work to do. So what happens here is you can think about it this way. If you factor out the x, you have two things. The x's will cancel out, and you have, oh, this is really just a graph of 5 plus x, and it's undefined at 0, because these will cancel out. The graph of 5 plus x is this graph right here. And if you remember your rational functions, when stuff cancels out, that's when you have a hole in the graph. So that's what this picture shows you. There's a hole in the graph. Right? But once you cancel this out, you can just substitute your 0 back in. Because now, substituting 0 into just this equation gets the value of 5. And that lets you know, hey, everywhere around this point is a graph, right? There's a hole. Limit doesn't care about the hole. It just cares what happens as you get close to 0. As you get close from both sides. It looks like it's going to 5. So, reducing that hole, canceling it out, makes the limit work. That's what's going on here. So, like, oh, I got 0 over 0. It doesn't work. Let's fix it. I'm going to factor x plus 3 over x. These cancel out. And now I have the limit as x approaches 0 of x plus 3. Substitute that 0 in, and you get 0 plus 3 equals 3. That's the limit of this function right here. It'll be the same thing on the next one. If I substitute this 3 in, I'm going to get 3 squared minus 9 over 3 minus 3, which is 0 over 0. Again, cannot solve that. I can't just stop there. I have 0 over 0. I got more work to do. We'll factor. The top here factors into x minus 3, x plus 3. And the bottom factors into x minus 3. X minus 3 is reduced. I get the limit as x approaches 3 of x plus 3. And now we can just substitute our limit in and get 3 plus 3, which is not 6. So there we go. Okay. So that's how you do a limit with the value. So if you're taking a limit at a value at a constant like 2, 0, or 3, that's all you do. Substitute it in. If it works, you're done. If you get 0 over 0, you have more work to do, which in this case, this means factor. Now, limits at infinity are slightly different. So we handle these a different way. So limits at infinity, it is what it sounds like. It's telling you what happens as you get close to infinity. So limits at infinity is saying, hey, as the graph goes on to the edge, as your function goes to the edge of to infinity, what's happening? Or if I said limit at x towards negative infinity, it's saying, hey, as you go to negative infinity, what's your graph doing? That's all it is. And if you remember your rational functions again, that's the same thing horizontal asymptote would tell you. The limits at infinity, or negative infinity, is just the horizontal asymptotes. So, remember how you do horizontal asymptotes? Well, for the most part, it's the same thing. If you remember horizontal asymptotes from rational functions, there was like 3 cases. If the top power is greater than the bottom power, there was no horizontal asymptote. Now we're doing limits, so it's not the same. We're going to say it's infinity or negative infinity. Or it does not exist, but that's a separate thing. If the bottom power is bigger than the top power, so I probably should give an example of this, right? So top bigger than bottom, something like x squared plus 1 over x plus 2. Right, top power is bigger than the bottom power. In this case, would have infinity or negative infinity. We'll talk about that more later. Bottom bigger than top would be like, hey, 2x over x squared plus 1. In this case, it was the limit equals 0. It was the horizontal was y equals 0, but we're talking about limits, so limit equals 0. And then if they're the same, bottom equals top. So something to this effect: 3x minus 1 over 2x plus 4. In this case, it was the ratio of these two. So the limit equals the ratio. So those are 3 cases of limit and infinity. It's if you're doing rational functions. It's top bigger than the bottom is infinity or negative infinity. Bottom bigger than top is limit equals 0. And if they're the same, it's the ratio. So let's look at the example here. Now again, this is a rational function. So since it's asking limit negative infinity, positive infinity, it's the exact same answer. I just got to figure out which of these 3 does it qualify as. In this case, they're the same. They both have power of 1. So this here, 2 minus x over 1 plus x. All we look at is this power here. So I have top equals bottom. So I look at the ratio. Now the ratio here is not these guys, it's these guys. Like the ratio here would have been y equals 3/2, or in this case limit equals 3/2. So the ratio of this over this is going to be negative x over x, which is negative 1. So limit as x approaches negative infinity, I can now draw an arrow. Negative infinity of f of x equals negative 1. And to be the same thing for as x approaches positive infinity. It works that way when it's a rational function. And if you want, we can look at the graph. So I already have it set up on my calculator here. So there's a graph, I'm going to hit graph. You can see both graphs, right? Like, let's look at negative infinity. So as we go to negative infinity, our graph's going toward negative 1. As I go to positive infinity, this way, our graph's going toward negative 1. So if it's a rational function, it works the same both ways. Now, if it's not a rational function, that's what's going on here. The best thing to do is to graph it. If you don't want to graph, you could try to sub in a big number. Let's see what happens. Oh, we'll do both cases here, but the general idea, if it's not rational, you graph it. If it is rational, like it is here, that's a rational equation, right? F of x over g of x, some function where you have dividing. If it's rational, you just do horizontal asymptotes are equal to, equals to the limits at infinity. So if it's a rational function, you can do that. Just look at the horizontal slope. If it's not a rational function, there's those rules don't apply anymore. You just have the best thing to do is just graph it. So let's graph this. It's an exponential function, right? So let's graph this. So you might have forgotten how to graph this equation here. So a couple things. Let's make it a little easier. Let's move 3 to the back. So it's negative e to negative x plus 3. Now that's just a vertical shift. That's all that plus 3 is. Let me make it a little nicer right there. Looks like it might be part of the horizontal. There we go. So this is just a vertical shift. It's this graph you have to remember how to do. So let's start off easy. E to the x. E to the x graph looks like this. Starts right there, it crosses that 1 and goes up. It's an exponential graph at 1. That's what an e to the x graph looks like. What does the negative in front do, if you remember? The negative in front is a horizontal flip. Sorry, a vertical flip. Or a lot of people call that an x-axis flip. So it's going to look like this. It's a flip upside down. I call it vertical flip because it flips vertically, and that's the whole thing I do. But it's technically not the x-axis flip. So it's vertically, goes on there. How about the negative right there? That's a y-axis flip. I call it a horizontal flip. So it's a flip it left and right. So let's flip it across the y-axis, right? Here's my x, here's my y. So we're going to flip it this way. So I'm going to graph something like this now. Right, again, we're flipping it left and right. So it's kind of like this. There we go. Took me a second to get it in my head. So we're going to flip it upside down, then flip it left and right. Our graph looks like that, and then all we have to do now is move it up 3. So our final graph, this graph right here is going to be that thing with the horizontal asymptote at 3. That's what that line's about. And then our graph's going up like this. So right now that crosses that too. But you didn't need that part, doesn't really matter. This is me showing off. This is y equals 3. That is actually very important. Okay, so that's how this picture will be graphed. You move the 3 to the back. This makes it a little easier to see. How do you graph this? Well, it's a normal e to the x graph. You just have to flip it upside down and left and right. So it's like this, and then we move it up 3. So normally you're at 0 here, right? Like 0. Then that's the vertical shift. So up 3. Okay, what's the limit as you approach negative infinity? Well, as you go to negative infinity, remember this is negative infinity is right here. Right? That's positive infinity. Remember, negative infinity is just literally where it's x going to negative on this side. What's my graph doing? It's going down to negative infinity. As I go positive infinity, as I go this way, what's my graph doing? Well, it's being capped by the horizontal asymptote. So as I go positive infinity, my graph's just going to be 3. That's how the limits work. So that's how you do it by graphing. Let's talk about how you sub a big number in. I'll start with the big one. If you want to think about it this way. Now it's the same rule as I said earlier, right? If the first rule of limits is plug a number in, well, you can't do that here because this is not a number. Infinity is like an idea, it's a concept. But what you can do instead is plug a big number in. Plug in like 100 or something, 1,000. Pretend it's like 100. What happens when I plug in 100? I get this: 3 minus e to the negative 100. Well, what's a negative power do? It flips it. So I get 3 minus 1 over e to the 100. So this is what we have to think about logically. Remember, if this is infinity, not 100. It's a big number. It's like goes on and gets greater and greater and greater. It's 1 over a giant number. That's just getting bigger and bigger. That's essentially 0, right? If you divide 1 by a giant number, it's going to be 0. So all this is turned into 0. So you just get 3 minus 0, which is 3. It's the exact same answer I got right there. If you want to get the other side, the limit as x approaches negative infinity of 3 minus e to the negative x, right? So let's pretend it's like negative 100. So when I substitute it in, I get 3 minus e to the negative times negative 100. Well, those double negatives cancel out. You just get e to 100. Well, e to 100 is a massive number. So you got 3 minus a really big number. Again, a big number that's getting like bigger and bigger and bigger, right? So this is, just think about it logically. 3 minus 1,000, right? It's negative 997. So this is a negative big number, also known as negative infinity. All right, that's what we got. It just gets bigger and bigger as the numbers grow. So that's how you can do it by trying to think about it logically by plugging a number in, a big number to represent negative infinity, and a big number to represent 1,000. But the most common way of doing this is by graphing. Anyway, that's the lesson.